Okay, grade 11s, we're going on to the second last video for the trig section, and this is still with general solution, but it's called co-ratio general solution. And as you can see in the title, it's obviously got to do with co-ratios. Remember the relationship between sine and cos, and when they add up to 90 degrees. So don't forget that when you're working with sine of 90 minus an angle, you can change it to cos of that angle. Now it goes the other way around as well. You can change cos of an angle to sine of 90 minus. So they go both ways. They're interchangeable. And remember, sine of 90 plus x is also cos x. Cos of 90 minus x becomes sine x. And then we've got cos of 90 plus, it's the exception, it becomes negative sine x. All right. This note will be posted on the Google Classroom as well. All right. So now let's just look at this example. Cos x equals 3 sine x. In this situation, so this is not new stuff. In this situation, I can divide by cos on both sides because I've got cos x sine x. And so that will make an tan x when I divide it by cos. I can get cos by itself, and then I can do my general solution. But, okay, so, well, in this case, it's x and x are the same angle. But cos 3x sine x, 3x is not the same as an x, so we can't divide. Absolutely, hugely essential here. You cannot divide by cos x to make a tan x. Right? It's only when you have the same angle. Cos of 3x, sine of 3x. Cos of x, sine of x. Cos of 50, sine of 50. Cos of 1,000,000 x, okay, sine of 1,000,000 x. Then they're the same. But if they're not the same, 3x to x, not the same, you can't divide by cos to make a tan. We have to do a co-ratio general solution. All right, so we use the co-ratio relationship. Now, you can change either. My preference is to always change the one on the right-hand side, but that's completely up to you. If you prefer to work with coses or you prefer to work with sines, that's fine. All right, so cos of 3x sine of x. Okay, I'm keeping the 3x as is, but going back here, a sine x can be changed. Let's just change the color here. A sine x can be changed backwards into a cos of 90 minus that angle. So sine x is changing to a cos 90 minus x. So once you have the same name, so I'm calling it very slang word here, name, it's the ratio, cos, on both sides, you can drop the cos and apply your general solution rules. And the reason is because it's saying to us here, cos of something equals cos of a different thing. Cos and cos are the same. It means those two other bits must be the same because that's the nature of what the equal sign means in maths. They are equal to each other. So if half of the right equals half of the left, same bits, the other stuff must be equal as well. All right. And then you don't forget, as soon as you drop a cos, sine, or tan, you have to do the general solution. Now remember, for cos, in this case I'm working with cos, it's going to be plus minus. So the left-hand side stays is. It's the right-hand side that is always the plus minus, or wherever the information is that we're working on, whether it's sine, cos, or tan. We always work on the right-hand side with the general solution. Right, so we have our angle of 90 minus x and our angle of 3x there. So we're going to split it into the plus minus, remember, because cos is positive or negative. So it's going to be positive 90 minus x or negative 90 minus x plus the k360. And don't forget to tell me somewhere that we have an element of integers. And then all we do is we need to just get all the x's to one side. So I'm going to take my x this side. It becomes 4x. 90 is going to live there by itself plus the k360. Then I'm going to divide by 4. So I'm going to get x. 90 divided by 4 is 22,5. And don't forget, when you're dividing, you have to also divide the 360. On the other side, don't forget we need to distribute in negative 90 and then positive x. We're going to take the x across. It will be 3x minus x on the left, and we'll get negative 90. So you end up with a 2x. You're going to divide the 2 in, and you're going to get negative 45 and positive k180. All right. So it's really the same once we get to this point over here. But to get to that point, we have to do a little bit more work than what we've had to do with the previous examples. All right, so let's go on to another type, and then I'll do a couple more examples of these. All right, so when we get onto this example, I'm going to put it up now. There's a reason it's hidden. I just want to remind you that sine of a negative angle is negative sine of that angle. Cos of a negative angle, remember, it does not get affected. It's just cos of that angle. Tan of a negative angle is affected. It's negative tan of that angle. All right, so just like before, we can also go the other way around. So if you have negative sine of an angle, you can make it sine of a negative angle. If you've got cos of an angle, you can pretend you have a negative angle within there. If you've got negative tan of an angle, you can then make a tan of a negative. Okay, so you can work the opposite direction. So the purple's going from negative, expanding outwards. The blue is going back. Okay, so when we're working with, oopsie, that's a big eraser. When we're working with it, we are working with a reversible situation here. Right, so I'm just going to block off those two main ones. The cos one, it's a bit silly because if you've got cos positive, don't try to bring in a negative. All right, so I'm going to move over this way now. So what if we have a situation like this? We have sine of 3 theta plus 30 and cos of then a different angle, 2 theta. Now, firstly, we've got sine and cos, but of different angles, so we're not allowed to divide by cos because they don't have the same angles. So I'm going to change the one on my right-hand side to a sine. So I'm following my co-ratio rules that cos of an angle is the same as sine of 90 minus that angle. Now, that negative in front here is still going to live there. Okay, but now we have sine angle equals negative sine angle. If you think back to the previous slide's example, you had cos angle equals cos angle. We could drop the coses, that's it. But here we can't drop the sines just yet. Why? Because sine is not equal to negative sine. Positive R1,000,000 is not the same as negative R1,000,000. If you have positive R1,000,000, you're rich. Negative R1,000,000, you owe the bank a lot of money. So they're not the same, so we need to adapt it, and that's where we're going to go here. So in this case, I'm going to take this one. I have negative sine of an angle called 90 minus theta. So I want to go back into the negative. So all I need to do is distribute that negative back in. So that's the same as saying sine of a negative angle. I'm putting it back in. So that can change to sine of negative 90 plus theta. Okay, so that's what's happened here. All right, so we've taken sine of a negative angle becomes negative sine of the angle. We've used that idea, but now we've done the reverse. We've got the negative sine angle. We're putting it back into the bracket. So you can only do this for sine and tan, because for cos is not affected by a negative. So we don't want to bring back negatives for cos. But for sine and tan, we can. All right, so we're going to bring it back in, and that's the step that I got over here. Right, the negative 90 plus, oh sorry, not over here, it wasn't theta, it was 2 theta. I lost my 2. All right, so we have sine of 90 minus 2 theta. We're putting the negative back in, and we end up with sine angle equals sine angle. So it's sine bracket, sine bracket. There's no negatives in front. They literally are identical except for their brackets. But now we can actually drop the sine and apply the general solution rules for sine. Now sine is a bit yuckier because we end up taking the theta plus 30. That stays on the left. It's this right-hand side angle that gets the general solution. So it's the angle plus K360, or it's 180 minus the angle plus K360. So it's a little bit more work here than the cos one. So then all you have to do is get all the numbers to one side, like the angles. Okay, so angles to one side. So I'm taking the 30 degrees across. I'm taking the 2 theta across. So it's 3 theta minus 2 theta is theta. Negative 90, I'm going to take off another 30 when I bring it across, is negative 120 plus the K360. On this side, we've just got to watch out. We have a negative going into a bracket, so it actually becomes 180 plus 90 minus a 2 theta here. Then I'm going to take that 2 theta across. It's going to become plus, so it's going to be 5 theta. And I'm going to bring that 30 across. It becomes negative. So I end up with 180 plus 90 minus 30 is 240 plus K360. But the problem is I have 5 theta there. So I've got to divide all the numbers by 5 on the other side to get my general solution. All right. One last example, and then I'll go on to a separate page that you can copy down the examples from. So cos 2x minus 10 equals sine x minus 40. So the problem is I've got different angles that go with sine and cos. So you either need to change both to sine or both to cos using the co-ratio. Again, I prefer to change my right-hand side. So the sine x minus 40, I'm changing to a cos 90 minus that bracket. Then I've got cos bracket equals cos bracket. So in the next step, all I've done is just sorted out that bracket. So 90, and then we're going to distribute in that. So it's going to be 90 plus 40 is 130 minus an x. And then once I'm happy and I've got cos bracket equals cos bracket, I can drop my cos and I immediately apply the general solution. And the general solution for cos is plus minus the angle on the right plus K360. And then I've separated into a positive and a negative section. So the positive section is just my angle plus K360. In my negative section, it's negative of the angle plus K360. And then all we need to do is bring the 10 across, bring the x across. So I get 3x equals 140. Divide everything by 3, so we divide the 140 and the 360 by 3, and we're left with our general solution. Then here I've got to distribute the negative into the brackets, and it becomes negative 130 plus x. I then bring my 10 across, I then bring my x over to the other side, which means I get x equal to negative 120 plus K360. That's my other solution. Remember, for a cos graph that I've discussed before, okay, even though it's symmetrical, in this case, something's happened. I mean, we're working actually with a cos and a sine graph. So one will be talking about, let's say, the 46, and then it's going to be every 120 degrees after. Now, what that's talking about is there's actually two graphs here. It's a cos graph and a sine graph together. And it's saying where are these two graphs going to meet. We will find that they meet at 46,67 degrees and then every 120 degrees before and after that. And then they will meet at negative 120 degrees and every 360 degrees after that. Okay, so understand what the question is saying to you. You started off with two different graphs, cos and sine, so they're saying where do they overlap? And in order to solve that, we play around, we manipulate a little bit, and that's how we do it. Okay, so I'm going to go on to some textbook exercise or textbook examples on the next page. All right, so I'm using the examples from the textbook, but not the textbook method. Remember, the textbook method is using something called a quadrant method. You're welcome to go through it and explore it. You're welcome to Google it, go on YouTube for it. But in terms of what we're working with the equation method. So I'm doing the textbook examples with the equation method. Your textbook is setting them out differently. All right, so this example from page 138 in your textbook has sine theta minus 20 equals sine theta. So we're starting off easy. Sine and sine, we're just practicing the dropping when we have the same ratio, the same name. So we have sine and sine there, which means that our angle and our angle are the same. So I'm allowed to go theta minus 20 degrees equals. Now, just be careful with sine. Let's just move this up. We need some space. We have theta minus 20 degrees equals theta plus k 360 degrees, or we're going to have theta minus 20 degrees equals 180 minus theta plus k 360 degrees. All right. And so I'm going to take the thetas across. We end up with 0 thetas here, which we'll come back to, is 20 degrees when I take that 20 across, plus k 360 degrees. So when you end up with a 0 theta, it means that for this part of the question, there is no solution. That's it. Done. So then we look at the other side. So I'm going to take my 20 across, bring all my numbers together, and bring my theta across. I get 2 theta is equal then to 200 degrees plus k 360 degrees. So I'm going to get my theta by itself. So I divide all the numbers by 2. Whereas on the other, not even on the other side, but here, when we bring the 20 across, it only affects the number directly because the k 360 is not a like term there. Remember, for division, we don't need like terms. We can divide any sort of term that is numerical with another number. Right, so I get 100 degrees plus k 180 degrees. Now, again, understand what this is saying. These two are two graphs, two sine graphs. One is the original sine theta. The other one is a sine graph that has had something happen to it. Theta minus 20. We're going to look in the graphs in a little bit, and so that means it's shifted left or right. And so when we have two graphs, they're saying to us, where do these two graphs meet? The only time we can see where they meet is going to be when our angle on our graph page, on our grid, on our scale is 100 degrees, and then every 180 degrees before and after that. So they'll meet at 100, and then they'll meet at 280. Then you add 180 to that, so that's going to be 460. So every 180 degrees to the positive, they're going to meet from 100, and then if you go 100 minus 180 at negative 80 degrees, they're going to meet. And then keep subtracting 180, and they're going to keep meeting. All right, please don't forget that k is an element of integers. So when we're looking at where do our two graphs meet, so if this is the sine graph on its own, and then this maybe is the sine graph that has moved, it's going to be at 100 degrees. And then the next time they're going to meet, they'll be at 280, and then 460 over here. But then remember, it's going backwards as well. So then we take off 180 from here, so that could be negative 80. and then the next time they're going to meet, and the next time they're going to meet. It's going to be 180 degrees apart. All right. So now the next example is going to use tan. All right, so this is question B of the same example on page 138. Again, now we're just practicing our use of our knowledge of if we have tan equals tan, then our angle is equal to our angle, but with the general solution. Tan's nice because remember it's just theta plus 10 equals, then the right-hand side angle gets the general solution. All right, and so then we have k is an element of integers. You can put it wherever you want there. I'm going to bring the 10 degrees across. I'm going to bring the 2 theta across. The 2 theta is going to subtract from theta, and my negative 10 is my 10 is going to become negative on the other side and subtract. All right. Now, just to stop you there, just think of what this k means. This k means how many hops. I can do a positive 1 hop of 180. That means going forwards. Or I can do a negative 1 hop going backwards when I'm looking for points. So this positive k or this plus k can end up being negative or positive depending on if we're going forwards or backwards. So we always just keep it plus k 180 because the k changes anyway to positive or negative according to our hops. So always keep it as positive 180 or positive k, should I say, positive k 180, positive k 360. Okay, so in this case, we are going to be dividing everything by negative 1 to make that theta positive. That's going to become 40. So we're dividing 180 by 1. We leave our k as positive because, again, we can substitute a negative or positive into it. So the nature of the k does not change. And that's our general solution. Again, this B is saying we have 2 tan graphs. Where are they going to meet? They'll meet for the first time at 40 degrees and they're every 180 degrees after that. All right, the next one's quite a mean one. It's also on page 138, example 35. But they leave you stuck with a situation that's a bit hard to get out of using your negative angle rules. So cos theta equals negative cos 2 theta. Now, if it was a negative sine 2 theta, I could have put the negative back with the angle. But because cos of a negative angle makes a positive cos of that angle, I'm never going to be able to get that negative put back in. I can't just put it back with the 2 theta because if I have cos of negative 2 theta, once we apply my negative angle rule, it will become cos of 2 theta. Cos is not affected. So we can't get back to the original. So the best thing to do in this sort of situation, it's a very rare situation, is to work with a co-ratio split straight away. So sine of 90 minus 2 theta, right? But then we still have cos and negative sine. So I'm going to change this one on this side also to 90 minus theta. And sine, so now I've got sine bracket equals negative sine bracket. So it's like the example I did a few slides ago on the white page where I can actually now incorporate that negative back in because sine, you're allowed to do that. Sine and tan you can, cos you're not allowed to. So it becomes sine of negative 90 plus 2 theta. Bring that negative back in. So then now we have sine and sine, so we can make the angles equal to each other. Let's make sure to leave some space. So I have 90 minus theta is equal to my angle plus k 360 degrees. But don't forget, we have or my left-hand angle is equal to 180 minus my right-hand angle plus k 360 degrees. So let's deal with the left-hand equation first. I'm going to bring this 90 across and bring the 2 theta that way. So I'm going to get negative 3 theta equals negative 180 plus k 360 degrees. So I'm going to divide by -3, so that gets me to 60 degrees. Remember, we keep it positive k, and 360 divided by 3 is 120 degrees. Then here I'm going to bring, well, first I've got to distribute. So I'm going to keep the left as it is, and I'm going to make it 180 plus 90 minus 2 theta plus my k 360. I'm going to bring my 2 theta across. Let's use a different color. 2 theta across. It's going to become theta. And then I'm going to have 180 plus 90 is 270. And then I'm going to subtract the 90 again. I'm going to get 180 degrees plus k 360 degrees. All right. And don't forget, somewhere around, tell us k is an element of integers. You'll see that it ends up getting you, in a lot of cases, the same or similar answers as what the textbook gave. But sometimes the textbook has extra solutions that aren't needed. So the solutions I'm giving you here are perfectly fine of what you need. Okay, so please follow the equation method unless you want to teach yourself the quadrant method, which you're welcome to do in your own time. All right, the last example that I'm going through is example 36 on page 139. It says solve for x where sine x plus 20 equals cos 2x. So again, we have sine and a cos of different angles. If they were the same angle, you can divide by cos and make it a tan. But in this case, we're going to have to work with a co-ratio. You choose left or right-hand side. I like to make the right-hand side different. Okay, sorry. So then I've got sine, so then I can make my angles equal to each other and apply my general solution straight away. Don't forget the or. X plus 20 is going to equal 180 minus that angle. Sorry. All right, so then I'm going to bring all my numbers to one side, my x's to the other. So it's going to be 3x equals to 70 degrees plus k 360. And then we're going to get x is equal to 23,33 degrees plus k 120 when we divide everything by 3. Then on this side, we're going to take our numbers over and we need to distribute at the same time. So I'm going to get, well, let's just wait to bring that one over. Let's not jump too many steps. So x plus 20 equals 180 minus 90 is 90. Plus a 2x. So we're going to bring the 2x across. It's going to become negative x equals 70 degrees plus k 360 degrees. And then so x is going to be negative 70 still plus k 360. You can put a minus k 360. It really makes no difference. But it's a perfectly set rule that you can keep it always as plus k 360. Can tell us somewhere that k is an element of integers. All right, so now I want you to work through your exercise 12. It's on page 139. Try A, C, D, G, I, but when I post the memo, I will post all of the answers, but I'll just walk you through those few as well as the extra ones. So I will do a video walkthrough of it, but I will post it in PDF form as well. All right, so that is the last bit of the general solution. And then I'll post the memo up, and then there's only one more video left of trig.